All right, let me begin with a word of prayer. So, Heavenly Father, we thank you for this class again. I just thank you for the students. Just ask you to bless our work this morning, help us to glorify you what we do, and just help the students ask good questions as they think of them, Lord. In your name I pray, Lord Jesus. Amen. So, made a mistake at the end of class. That's what I get for hurrying. So I was integrating z squared ds over the half cylinder. You guys remember this thing? Where basically that was the y-axis, and so this thing had equation like x squared plus z squared equals to 4, and this was y equals to 0, and this was y equals to 10. And so we parameterized this thing, and we figured out that, among other things, the ds was, ds vector. Can you guys remind me what that was? It was what? There's a 0 here. Was it 2 cos beta? 2 sine beta, right? 2 cos beta, I think. But the parameterization was 2 cos beta, 2 sine beta, 2 sine beta over here, and a y in the middle, right? And I think we figured out we had to put, which we have to put first, the beta or the y? I can't remember. Y beta oriented upward. Anyway, so we figured that out. We calculated the vector surface area element, and then I quick rattled that off. Now, to be clear, this, of course, I'm missing my dy d beta here, right? So the magnitude, essentially, of ds is 2 dy d beta, and that's what we use for the surface, the scalar surface area element. So that's why this goes here. And why is it 2 sine beta squared? Well, that's because that's the z formula, right? So that's the integral I should have done at the end of last class to calculate the integral of z squared over that half cylinder. And of course it, I mean, any question or? So let's see here, just to finish it here. We've got ourselves what, 4 squared 8. Let's see, y integrates to 10, and then you've got integral from 0 to pi of sine squared beta d beta. But let's see here. And I don't know, we could use my trick, or we could just do 80 over 2 is 40, integral from 0 to pi of 1 minus cosine 2 beta d beta. Of course, this integrates to 0 because that's over a full cycle of cosine, and the other just gives me a pi. So the answer should have been 40 pi. All right, so there's that. So just a reminder, some paper towels stuck on the board. That's different. So just a reminder, we have 2 major theorems, right? What are our theorems? The big ones that we're learning right now would be, of course, the integral of f dot ds, right, over the boundary of some solid region E is equal to the triple integral over the solid of the divergence of the vector field, right? And then the other interesting one, and this of course is the divergence theorem, and the other one that we learned was that the integral around the boundary of some surface of f dot dr, the line integral, is actually equal to the surface integral of the curl of f. All right, so those are the 2 big two big guns, so to speak, we have. Of course, before that, we also had the fundamental theorem of calculus for line integrals, and its importance should not be discounted either, right? The other very important theorem we have in this material, I suppose I shouldn't really discount it, is that we have f of q minus f of p is equal to the integral. If you've got a curve that begins at p and terminates at q, and you're calculating the line integral of the gradient of a scalar function, we have that, right? And I suppose you could also add Green's theorem to this list as well, right? What's that? No? So let's look at example 1. Let's suppose we have f equals to, x cubed, y cubed, z cubed. All right? Let's calculate the flux of this vector field through the solid, the boundary of the solid. Let's let E be the solid that's just 0 to 1 Cartesian product with itself 3 times. Or maybe it'd be good for us to, forget that, let's do something a little more exciting. Let us do 0, 1, Cartesian product, 0 to 2, Cartesian product to 0 to 3. That way you can better appreciate this notation. What does that notation mean? Well, that notation would mean the set of all x, y, z such that 0 less than or equal to x less than or equal to 1, 0 less than or equal to y less than or equal to 2, 0 less than or equal to y less than or equal to, my bad, z. I did y twice. Y. 3, there you go. So there you go. It's not a cube anymore, but it's a, right? It's a rectangular solid, if you like. And I'd like to know what's the flux of f through the faces of E, you know? How should we do that? We definitely, I hope this just hits you over the top of the head with I should use the divergence theorem, because we don't want to calculate 6 surface integrals, right? At least I don't. Not today. Not in one example. So here we go. The integral of f dot ds over the boundary of E is equal to the triple integral. And here we can set up the triple integral pretty easy, right? Integral from 0 to 3, integral from 0 to 1, my bad, 0 to 2, integral from 0 to 1. That's how we set up the bounds here. What's the divergence of f? Yeah, the divergence of f is partial x of x cubed plus partial y of y cubed plus partial z of z cubed. And that works out to what Shane just told me, which was 3x squared plus 3y squared plus 3z squared, right? dx, dy, dz. I propose we pull a 3 out. Oh, wait a minute. No, I don't do that. Let's integrate. What happens when we integrate? So the integral over x pulls down, oh man, wait a minute. I better think about this. Duh. So the 3x cubed integrates to 1, right? The 3y squared integrates to 3y squared. The 3z squared integrates to 3z squared. Because we're just integrating dx from 0 to 1, which just gives me a 1 on the y squared and the z squared type terms. Whereas the 3x squared anti-differentiates to 3x cubed over 3, which gives me a x cubed. evaluated from 0 to 1, just give me a 1 there, right? Now when I do the y integral, I've got integral from 0 to 3 of, well, this 1 integrates to 2, and the 3y squared integrates to what? 8, right? And then we've got plus 6z squared. You're probably wondering what I just did. I'll show you, like, integral of 3y squared dy from 0 to 2 is 3y cubed over 3, evaluated from 0 to 2, also known as 8. So that's how this guy went to that guy. The other two, it's more boring. It's just because the integral of dy, right, from 0 to 2 is 2. So since the 2 and the 6z squared aren't interacting meaningfully with the integration over y, we just end up multiplying by the length of the integration. And then finally, what we got? We've got a 10 times 3, and then plus what? Plus 6 over 3 is 2 times z cubed, evaluated from 0 to 3 gives me a 3 cubed, which is 27. So anyway, I get 54 plus 30, 84, I think. All right. Any questions? No? All right. All right. How about this? Consider f equal to, let us say, z squared plus x squared y cubed sine of z. Cosine of z. All right, and let us consider the curve in the xy plane. All right. As pictured. Let's see here. Here's the question. Calculate the integral along that curve of the vector field. Let me share with you a simple calculational technique for calculating curls faster. See, this is fairly obviously a Stokes theorem question, given the conversation, right? Like, I don't know the details of the curve, right? I just know it's a curve in the xy plane, right? So all I really know about that curve is that z equals 0 for the curve, right? That's pretty much all I know. And it's a closed curve. Now, if this vector field was conservative, we'd know that the answer is 0. However, it's not conservative. It's not a conservative vector field. Why? Check this out. So the curl of f, but it's almost conservative, is really the curl of the vector field x squared y cubed cosine z, right? Plus the curl of the vector field z squared 0, 0. Notice that the first term is manifestly conservative. Why? How can you just see something's conservative just by looking at it? You're like, you made this example up before class, that's how you know. Trust me, I'm not that prepared. Wait a minute, you're doing course evaluations. Never mind. I'm very prepared. Instructor is very prepared for class. No. You should have more faith in yourself. You should say something like, no, there's no way the instructor could have been prepared for us. You know, right? Anyway, so pretty much if the x component just involves x, if the y component just involves y, if the z component just involves z, the curl of that is 0. Because the curl is only, what is the curl full of? The curl is full of partial derivatives of other components with respect to other variables. So like the x part of the curl involves z and y derivatives of the z and y components. The y component of the curl involves x and z derivatives of the x and z components. The z component of the curl involves x and y derivatives of the x and y components. So what that means is if the x, y, and z components are respectively just functions of x, y, and z, the curl is automatically 0. If you don't believe me, just look at this and go, well that is nabla of 1/3 x cubed plus 1/4 y to the 4th plus the sine of z, right? So there you go. There's a potential function for this that works on all of our 3. It's conservative, right? So what's the curl of the gradient? Remember this identity? A couple of identities in here you need to know. One of them's this. The other one that's good to know about like this is that the curl of a, wait a minute, I'm trying to remember. The divergence of a curl, I should say. These are 0, right? So if you ever run across one of those, you know it's 0. So this piece, gone. And what is this? Well, what is this? This is x hat partial x plus y hat partial y plus z hat partial z acting on what? Well, cross product, so to speak, with x with z squared, right? How does that work? Well, let's see here. So I guess I should really just call this z squared x hat. Of course, you could write down your determinant mnemonic, like whatever floats your boat. But we should all agree on the curl being what I'm about to write down. Sorry, guys, over there. I use red where you can't see. My apologies. So let's see here. X hat cross x hat, 0. Y hat cross x hat is minus z hat, but partial y of z squared, nothing. So the only term that matters is this on that. All right? Z hat cross x hat is y hat. And we've got partial z of z squared. In other words, you got yourself a 2z y hat. Or if you like, the curl is 0, 2z, 0. All right? So what does this mean? We can apply Stokes theorem, right? We can apply Stokes theorem to this, let's say the surface that bounds the curve is in the xy plane, right? The surface which bounds the curves in the xy plane, where z is equal to 0, right? If I think of C as being this little guy right here, C is the boundary of S, so constructed. And so my Stokes theorem becomes the integral over S of the curl of f dot ds, right? But how does that actually go? That's the integral over S of 0 to z 0 dot product with what? Well, dx dy z hat, right? Which is 0 for a couple different reasons. See, because one thing is, I really should put what here? I should really put 0 there because we're calculating the surface integral on the xy plane where z is equal to 0. So the curl is identically 0 on the xy plane. All right? And I think if you stop and think about that for a second, that makes more sense why this would be conservative on the xy plane, right? Because on the xy plane, this is 0, and you're just left with a conservative vector field on the xy plane. If you freeze z out, make z equal to 0, the part which is non-conservative is kind of gone. So anyway, short answer, integral 0. Now, if you picked a different loop for this, right? Like, let's see here. Can you guys tell me what loop could I give that the integral around the loop would not be 0 for this one? What if I did something like, I think if I did something, I'm trying to visualize it, guys. If I did something exceedingly silly, like maybe integrate around this square loop, right? Like, if you can imagine this being the loop, right? This being the curve. Can you guys see that over there? Okay. Well, in that case, oh no, I'm thinking about it wrong. Just a second. I need a loop. I need a loop whose basically I need the ds vector to be something like blah y hat, right? That's not the right loop. I need what loop? If I did like this, right, with the ds vector looking like that. So ds is literally like, you know, words here, dx, dz, y hat for this surface, right? And then so like the boundary loop would be this guy. For that, and suppose that this point, just for the sake of specificity, is 1, 0, 1, all right? So basically that's square. If we calculate the integral of the given vector field from example 2 around the boundary of this, let me call this square, I guess I call it S for lack of imagination, around the boundary of S, which is this square, the edge of the square, then by Stokes theorem, we have, it's the integral from 0 to 1, integral from 0 to 1, and what is the, son of a gun. Oh no, it's okay, it's okay. I thought for a second, I thought the curl was 0 again, because I played my cards stupidly, but I've only played my cards moderately dumbly. No, they're fine. So 0 to z0 is the curl, right? Well, anyway, let me get to the point. What's the dot product? What's the dot product of the curl with ds here? It's just 2z d dx dz. So that would integrate to like, 2 times z squared over 2, value from 0 to 1, and of course x value from 0 to 1. So also known as Oh, 1. Okay, well, there you go. So this vector field is not conservative. There's an integral around a closed curve, which is non-zero, right? And that's coming from the fact that the curl of this vector field is not 0. So whenever the curl is not 0, we can find a loop such that the integral around the loop is not 0. Any questions? All right, let me gaze upon my notes here for a second. See if I have any good examples to share with you guys. An idea which comes up a lot in second semester physics, which we probably should talk a bit about, because it is something I do like to test a bit on, is the idea of using symmetry to help with these calculations. All right. So let's look at something like that. Suppose, example 3 here, we're looking at the solid which is formed by like -1 to 1 cubed. So what that is the set of x, y, z such that -1 is less than or equal to x, y, and z, which is less than or equal to 1. So if you like, it's a cube, right? It's a cube of side length 2, which has got the origin smack dab at its middle, right? So an interesting question here is to ask something like, right, like, how about this? I'll make it maybe the trickiest version of this. What if I ask, what's the flux of F equal to x, y, z through that? And I'm find the flux of that, with ds as pictured, okay, just directly out. So how do you solve a problem like this? So first of all, this is pretty clearly a divergence theorem problem, right? This is not a Stokes theorem problem. I think we can agree. Yeah. So first of all, let's calculate the divergence of F. What's the divergence of F here? It's 3. All right, well, that's nice. So what if we look at the flux over the boundary of the entire cube? What's that? By the divergence theorem, it's the integral over the cube of 3 dV, right? Also known as 3 times the volume of a cube. Now, I hope you don't need calculus to calculate the volume of a cube. What's the volume of this cube? So like, for instance, this point right here in our system of coordinates, our usual system, would be 1, 1, 0. This point up here would be, I'm sorry, -1. Oh, wait a minute. My bad. It's I'll get it eventually, guys. It would be that. This one up here would be 1, 1, 1. So anyway, long story short, each side has length 2. As I said it in words, I didn't write it on the board, right? So what's the volume of the cube? I heard an 8. I'll allow it. So 3 times 8. So the net flux is 24. Now in physics, we talk about vector fields. They're always vector fields that have some sort of physical meaning, and so they come with units. For example, if you have an electric field, it comes in units of newtons per coulomb, because the electric field interacts with charge, and the units of charge are coulombs. So newtons per coulomb, when you multiply by coulomb, gives you newtons, which is a force, right? But in math, we talk about these unitless vector fields, and no one cares. I prefer unitless vector fields for calculus. It would be really annoying if I started using a system of units in every example, cluttering everything with units. Anyway, 24 units of flux. So, what's the answer? And why? What don't we want to do? I tell you what we don't want to do is to parameterize that little patch and actually do the calculation. I want no part of that. Although it wouldn't be a hard calculation.
Would the flux be 1?
The flux would be 1. Why?
Because that's 1/24 of the cube.
That's 1/24 of the surface area of the cube, yes. So if you look at the cube, right, there are 6 faces, and each one has 4 subfaces, if you will, right? And what makes this argument work is that this vector field, right, is what? It is symmetric with respect to all 24 of those subfaces, right? It points the same way out from the origin in every single one of them, because this thing looks like the hedgehog, you know? It's like, it's this way, and 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 they're out this way. I can't draw it 3-dimensionally. You get the, I don't know. I can't ever draw this thing, but it's every which way all at once. I need a model, you know. None of your hair is sufficiently spiky to illustrate. Oh well, if we lived in a different time. Yes, my son is the closest. No. That's Hannah's fault. She did that to you. We had crazy hair night at Awana the other day. Excuse me, not Awana. We don't do Awana anymore. It's Adventure Club, yes. But some of the kids' hair was pretty spiky, but not sufficiently spiky to illustrate this vector field. All right, so there's this. Let's do another example. Wait a minute, why am I using that? How uncivilized. There we go. It's better. I'm going to break here from the storyline. I want to break from this current storyline and do a 2-dimensional example for a change. All right, so example 4. Let's look at f of xy equal to, let's say, basically x comma y divided by x squared plus y squared, if that makes sense to you guys. In other words, to be explicit, this guy. Okay? I'd like to calculate calculate the flux, all right, of this vector field through the unit circle, well, through a circle of radius r. Let's calculate flux through, let's call it C sub r, which is you know, x comma y, such that x squared plus y squared equals to r squared, you know, counterclockwise. So you guys remind me, how did we calculate the flux of a two-dimensional vector field through a curve? What did we figure that out was? That was what? The integral along the curve. It was a little bit sneaky. If this was PQ, we didn't just integrate PQ. What did we do? We integrated, oh man, I have to look it up. This is something I don't remember. It's just a blind spot in my memory. Oh, hey, I keep forgetting to give you guys, I printed out mission 8. Anybody not have it? You have 2? You want 1? I recommend doing mission 8. When's this due? After Thanksgiving? Oh man, what'd I do that for? I've ruined your Thanksgiving. Now you won't be able to pay attention to your family because math is just more interesting.
It's supposed to be the day after Thanksgiving.
It's due the day after we get back. Oh, I'm sorry, I missed you guys. Our test is on. Oh. You already got one? You want our test is tomorrow? What? Oh. Quiz is Thursday. All right. Yeah. All right. So can anybody remind me how we calculate this while I'm searching through my notes vainly to find it? It's back in Green's theorem. Oh, I think it's, yeah, PDY minus QDX. PDY minus QDX is what we figured out. So, and that came from just taking the dot product with the outward normal. Remember, we figured out that outward normal switches x and y, and so when you take the dot product with the outward normal, you end up with this formula. Okay, so we can actually put this in practice. What's our parameterization here? Well, we have x is equal to r cos t, y is equal to r sine t. So dx minus r sine t dt, dy r cos t dt, 0 less than or equal to t less than or equal to 2 pi. That'll do the set up this integral right nicely. And what's the situation here? Well, we've got ourselves an integral from 0 to 2 pi. Now p, what is x squared plus y squared? It's not, well, 1 is the right idea, but r squared, right? It's r squared for the circle of radius r. So what we got here is x is r cos t, and then my dy is what? R cos t dt, right? And then we've got minus r sine t times minus r sine t. There's a dt, I'll just pull the dt out front. And then of course downstairs we've got r squared plus, well, we've got r squared. Well, hey, wait, the r squared, they cancel. This is just integral of dt. Look at that, 2 pi. Yeah.
But cosine squared minus sine squared isn't.
But it's not minus sine squared. Hooray. Yeah, if it's cosine minus sine squared, it wouldn't give me as much joy. Okay, that's cool. So that kind of makes sense, right? If you think about circle of radius r, and you think about the center, you can imagine field lines like this. I don't know why I'm not doing these two at once, but anyway. And so the field lines are like so. And now, why can I draw the picture like this, you might ask? Well, what's the divergence of this vector field exactly? Can you guys calculate? What's the divergence of this? What's the divergence of my f? two-dimensional divergence here, obviously, right? So we've got partial x of x over x squared plus y squared plus partial y of y over x squared plus y squared. How's that work out? Well, looks like we've got x squared plus y squared minus 2x squared divided by x squared plus y squared squared by the quotient rule. And then here we've got a x squared plus y squared minus 2y squared divided by x squared plus y squared squared by yield quotient rule. Add these together and 0. Because you have x squared plus y squared times 2 and minus 2 of those. So it works out to 0. Huh. So then if I apply the divergence form of Green's theorem, what happens here? Huh. So C is like the boundary of the, C sub r is the boundary of the disk of radius r, let's say. And I got my p dy minus q dx. The divergence form of Green's theorem says that's the double integral over d sub r of the divergence, right? Which in this context, two-dimensional context, is partial p partial x plus partial q partial y dA. Huh. But this is 0. Right? This is 0. So of course 0 integrates to 0, right? Yes? We agree? Did you guys catch up with me here? I'm sorry we're almost out of Calculus 3 to cover. It makes me sad. Man. There's another section or two in my notes. We'll cover those, but it'll feel like new material. But it's really just applications of what we're doing. But what did we just calculate behind me? Theta. Ah, you've seen through it. But 2 pi, right? So this is what? This is 2 pi, yeah? Huh. Looks like we need to set pi equal to 0 then. That seems problematic. What gives? This can't stand. 2 pi can't be 0. I didn't miscalculate the divergence. It really is 0. Can someone solve this mystery? This paradox? What's a paradox? It's a seeming contradiction. So I'm telling you this isn't really a contradiction because I've cheated you somehow. It's like Biden being president. Sorry, too soon? Oh, I'm sorry, it's been proved. What am I saying? Oh, how dare I?
Are you using 2 different definitions?
What's that?
Are you using 2 different definitions of the function?
No, it's something more basic. Green's theorem is true, provided that your vector field is, it's like basically it needed to be smooth, well, at least once differentiable, I think here, inside, both on the curve, which we're working with, in this case, the circle of radius r, but also in the entirety of the interior of the curve. There is a problem with this vector field at one point, but one point is all it takes to mess up Green's theorem. The origin is the source of this contradiction, because at the origin, this field is not defined. And that's where all the field lines are coming from. You see, the divergence is 0 everywhere except for where it matters, which is at the origin itself. At the origin, all the field lines come into existence and flow out from there. From the perspective of physics, a typical comment that I could make is that where the vector field is not defined is where the charge is. So what you're looking at essentially is like the electric field in 2 dimensions. This is what the electric field of a very long line charge looks like. It's reciprocal with distance. If you look at the formula here, the formula for this vector field could be written like this. It's nothing more than r hat over r. That's what this formula is. Because r hat, the unit vector in the outward polar radius direction, is you just take the xy vector and divide by its length. Okay? So you got one of those, but I see I've got an extra one, so I have to divide by r hat. That decreases as the reciprocal from the origin, all right? But you're right, Michael, this is exactly the same example that I integrated 2 pi before. But there it was different in the sense that let's see here. So if you look at this explicitly, the integral we just did is, let's see here, x dy minus y dx over x squared plus y squared. That is an integral we did before, isn't it? Yeah. But last time we did it, we interpreted that as basically being the integral of the differential of the angle function around the curve, and that's why we got 2 pi. So that's another way of looking at this. So, but that really is if we look at this directly, this is the work done by a rather different vector field, right? This vector field minus y comma x over x squared plus y squared is everywhere perpendicular to this one. It's the theta hat, essentially, divided by r, I think. All right, so let us continue on. So bottom line there, cautionary tale, if your vector field is undefined at even one point inside the region that you're working with, then you can't apply Green's theorem unless you take an account for the hole that's inside, let's say. Like, in order to do this, I would have to, instead of doing over the whole disk, I'd have to like punch a little hole out in here. I'd have to like kind of like take it inside. Like look at this annulus. On this annulus, the vector field's defined. And on the annulus, I could apply Green's theorem. But the thing is, no matter how small that inner loop is, you're going to pick up a minus 2 pi. It's funny. You're going to pick up a minus 2 pi. Like if I applied Green's theorem instead of on the whole disk on this like annulus, then you'd have the counterclockwise oriented outside edge, the clockwise oriented inner edge. You'd have a 2 pi integral out here, but you'd pick up a minus 2 pi integral in there. The 2 pi and the minus 2 pi cancel, and then the integral of the zero divergence over the area of the annulus is causing no contradiction. That's how it all goes. So what that means basically is that it's just what we calculated, which is that there's 2 pi flux going out from the circle, whether it's here or whether it's there. But we can't actually enclose the origin unless we're willing to expand our scope past just functions. All right, example 5. So the three-dimensional analog of what I just did, all right, we've looked at this example before, but it bears more discussion, is if we have f equal to basically x, y, z divided by x squared plus y squared plus z squared to the 3/2 power. All right, so this in spherical notation is rho hat divided by rho squared. This is the inverse square law. This is the three-dimensional analog to my example 4. And the cool thing about this is if we integrate over, let's say, the boundary of the ball of radius r, of f dot ds. Well, we can do that directly. Remember, what's the ds for for the sphere of radius r? We worked this out. What was it? It was ds was r squared sine phi d phi d theta rho hat, right? That is definitely the way to do these kind of integrals. Doing them in Cartesian coordinates is a drag, but you can. If you're more comfortable with that, you can do that. All right? It's up to you. Okay, so if I'm doing the whole sphere, I've got to integrate from 0 to pi, integrate from 0 to 2 pi, and I've got rho hat over r squared, because rho equals to r on the sphere, right? This guy is rho equals to r. So I do rho hat over r squared, dotted with r squared sine phi d, I did d theta d phi. And notice that the rho hat, right? So the only thing here is the rho hat dot rho hat gives you what? Gives you 1. The r squareds, they be canceling, and you got integral from 0 to pi of sine phi d phi, integral from 0 to 2 pi of d theta, right? And that gives us 4 pi. That gives us 4 pi independent of what?
Of the distance.
Yeah, independent of r. And you guys in your homework have calculated, right? Well, or you will calculate the divergence of r, of f rather. What is it? So you work it out. The divergence of this vector field is actually 0. So if I apply the divergence theorem, I think you see where I might be going with this. Well, the divergence theorem would tell me that this thing, right, is actually equal to what? The triple integral over the ball of radius r of the divergence of f dv. But what's that equal to? Well, this is 0. So this is equal to 0. Now, you probably see right through me at the moment, like, what am I doing? What's the cheat? Of course, 4 pi is not equal to 0. What's the rub? The origin, this example, this vector field is not defined at 0. Domain matters. Ignoring domain issues leads to contradictions. So these theorems, they do have strings attached. We do need like that the vector field is continuous within the region in which we're just, applying Stokes theorem or the divergence theorem. Because even one point where the vector field's not defined leads to a rather large contradiction, right? So the reason that this is illegitimate, right? Illegitimate, since f of 0 does not exist, cannot apply divergence theorem to f on the ball of radius r. Now, what could you do? What could you do? So if we can't apply the divergence theorem on the ball of radius r, what we could do is we could encircle the origin with a little bubble, and we could imply the divergence theorem on something like this. So here's like 0. So just basically right, so let's say this is, R1, and over here you've got R2, all right? And you could let, you could let your E be x, y, z such that, R1 is less than or equal to rho is less than or equal to R2. That's a spherical shell with inner radius R1 and outer radius R2. Okay? And the divergence of this vector field, well, it's 0 in that region, isn't it? Your homework problem. You'll prove this, okay? You'll prove this in the homework. If the calculation is very analogous to the one I did here. There's an easier way still, though, if I show you some things, which I will. But here we have the divergence of f is equal to 0. All right? So, fine, what we can do is say, all right, so the integral around the boundary of E of f dot ds is equal to the integral, triple integral, of the divergence of f over E. Now this, what I just wrote in green, it's fine. It's okay. Why is this okay? Very simple. The divergence of the vector field is not within E. It's outside of it. Right? It's safely been punched out of the interior of E. What's the cost of punching the hole out? The cost is now when we apply the divergence theorem, we have to account for the inner boundary. So the boundary has two pieces. It's got the outer piece and the inner piece, right? So what this gives you then is that the surface integral of f dot ds, along the minus the sphere of radius r1 plus the integral over the sphere of radius r2 is equal to 0. What does this all show us? This shows us that the integral over a sphere of radius r1, right, is equal to the integral of the flux over the sphere of radius r2. This is a deformation theorem. If we take one surface, all right, so here's the bigger principle, independent of this particular example. Let me write it down in a sentence. So it's basically, this is the theorem. If the divergence of f is equal to 0 everywhere in the solid region bounded by S1 and S2, then the flux through S1 is equal to the flux through S2. Assuming, of course, that we orient S1 and S2 to both be pointing in such a way that they define, well, I don't, how can I say it? I'm talking about, so S1 and S2 are consistently oriented, okay? So I guess that would, I don't know how to say it. I mean, I can say it. So what I mean in particular is that consistently oriented has to mean that there exists a solid region E such that the boundary of E is S1 union with minus S2, okay? That's the most convenient way for me to describe what I mean by consistently oriented, is that there exists a solid region for which S1 and S2 form the like inner and outer boundary. So let me put it in words though. What this is saying is that if the divergence of the vector field is 0, if we calculate the flux through one surface, if we take that surface and blow it up to another, just think about like